Welcome to the lesson on doubly and circular linked lists. In the last lesson, each node had one link called next that pointed only forward. This lesson adds a second link called prev that points back to the node before it. It also adds a second shape, a ring, where the last node links back to the first. With these two small changes, many jobs become much easier, and we will see exactly why. Let's start with a simple question. Why do we need a second link and a ring shape at all? To answer it, we look at one job that a singly list does very badly. This is what you will be able to do after this chapter. First, you can name every pointer that a delete touches. For a node in the middle, that is 2 links. At the ends, you may also fix head or tail. Second, you can walk the list in both directions. You go forward by following next. You go backward by following prev. Third, you can state the stop condition for a ring. A ring has no null at the end, so you need a clear rule that tells the walk when to stop. 2 more goals. Fourth, you can read one node byte by byte. You lay out its 3 fields, data, prev, and next, in memory with padding and 2 real addresses. Fifth, you can write and free both shapes and see you build a doubly list and a ring, and you tear each one down without leaking memory. One idea drives the whole chapter. A second pointer gives a second direction. The prev link lets a node undo its own insertion in big O of 1. No walk is needed to find what came before it. You already hold a pointer to the node with value 20 and you want to delete it. In a singly list, each node points only forward. To unlink 20, you must fix the node before it, but nothing points backward. So you must walk again from head to find the node whose next is 20. Step 1. The cursor starts at 5, the head. Its next is 8. 8 is not 20, so you advance. Step 2. The cursor is now at 8. Its next is 12. 12 is not 20, so you advance again. Step 3. The cursor is now at 12. Its next is 20. This is the one we wanted, so 12 is the predecessor. That walk took 3 steps. Now think about a bigger list. On a list of 1,000 nodes with 20 near the end, you walk about 1,000 steps, and that is just to delete a node you were already touching. So split the cost in 2. The pointer work itself is big O of 1. It is finding the predecessor that costs big O of n. Watch out for a common trap. You may think that holding the node makes the delete instant. In a singly list, it is not instant. With no backlink, you first pay a full big O of n search to find the predecessor every time. The fix is small. We add 1 field to each node. This field is a prev pointer and it names the node before this one. Now the predecessor is just X arrow prev. You read it directly with no walk at all. Think of a line of people holding hands with both neighbors. To remove one person, their 2 neighbors simply clasp hands directly. Nobody has to walk the line to find who was holding on. Now for the key idea. A second pointer gives a second direction. The X arrow prev link names the predecessor directly. So a no-node delete drops from big O of n to big O of 1 with no search, just 2 local writes. Close the chain into a ring, and that same pointer also removes the null at the end. Let's put the 3 problems side by side. On the left is what the program needs to do. In the middle is the cost with a singly list. On the right is how a second pointer helps. This first row is the main point. You want to delete a node that you already hold a pointer to. With a singly list, that costs big O of n because you must rewalk to find its predecessor. With a doubly list, you read X arrow prev directly, and the cost drops to big O of 1. The second row is walking backward from any node. With a singly list this is impossible because there is no prev field. With a doubly list you just follow prev, and each step costs big O of 1. The third row is walking a task list that wraps around like a scheduler. With a singly list you need a special case for the end of the list. With a ring there is no null wrap case. You stop when you return to the start node or after a fixed count. Keep the first row in mind because it is the main point of this chapter. With only a next pointer, deleting a node you already hold still costs a search. That search disappears once each node remembers its own predecessor.